All right, let's take a little historical side road here and talk a little bit about the history of our understanding of Earth's place in the universe and what we see when we look up at the sky. We're on our way to talking about Newton's theory of gravity, but we're in a gen ed course. We ought to give a little bit of a historical context here. It's not going to be a huge part of the course, just a little section where I summarize a lot of history in a very short period of time. So no calculations in this particular video. It's just sort of historical context. So we're going to talk about the historical sequence of kind of ideas about the Earth and where the Earth fits into the universe. So first of all, flat Earth kind of models, and then ones based on a spherical Earth where the Earth is the center of the universe, and then later on where the sun is the center of the universe, and the universe sort of planets and stars revolve around the sun, and then finally the viewpoint advanced by Galileo and Newton, in which case there isn't really any center of the universe that we can think of. So let's first go to the flat Earth kind of models and see what the motivation for them is. You have to put yourself back in the context of someone on the ancient Earth and imagine what you're doing. Well, of course, you look around and we know there are hills and valleys and stuff, but you can see obviously Earth is more or less flat. So the idea that Earth is flat makes a lot of sense if your observations are based only on like sort of what you see out in front of you. The second thing you spend a lot of time looking at is the stars. If you don't have electric light, once it gets dark outside, you have nothing to look at but the stars, and without much light pollution, they certainly are much more visible than they are in Danville or Lexington, where I live, where there's just a lot of light. It makes it hard to see the stars. One of the things you notice if you spend a lot of time looking at the stars, you might notice where certain constellations are in the sky, and as you watch them, you notice that the stars move around in circles in the sky. They rotate roughly around the North Star, and if you put those two ideas together, that the Earth is obviously flat and there are points of light moving in a circle in the sky, it's almost like the points of light are little dots of light in a dome that surrounds the flat Earth, and that dome is spinning as time goes on. So that's the idea of the original flat Earth models, or at least the ones that we know about from history. And the dome in which the stars were supposed to be embedded, of course, nobody knew what stars were. They were just little dots of light, and they were thought to be embedded on the surface of a spherical dome, which is called the firmament. And so here is a woodcut, famous woodcut of, this is supposed to be the flat Earth down here that humans walk around on. And then there's a dome that surrounds all of the Earth, and on it are placed certain dots of light, and those the whole dome rotates as time goes on, and that makes the stars move around to different positions. And I'm not sure what this fellow is doing. Somehow he's looking beyond the firmament into fundamental reality of the heavens or something like that. But in any case, this shows that ancient view of the universe. So that's the idea, or the starting point we're coming from here, of flat Earth models, where the Earth is the center of the universe. And in fact, the universe really consists, I think, in most of these models of just the firmament and what's inside it, which is the flat Earth. There were some problems noted with the flat Earth models. By Aristotle was sort of the leading proponent of this. Here are just a couple of the major ones. Travelers who went south on Earth began to see different stars that would be visible and were not visible in the northern hemisphere, or at least farther north than they were looking. And there's no way to explain that. If you look again at this woodcut, if the stars are spinning around attached to the firmament, someone who's over here near the edge or someone who's farther over on this side of the Earth, they should all be able to see all the same stars at every time. You shouldn't be able to see different constellations suddenly appear that you never see when you're in the north. So that was a problem. There's also the problem of they rise to different heights above the horizon, and that seemed to be inconsistent with the flat Earth model. Second thing, which is just being reasonable, the shadow of Earth on the moon during the lunar eclipse was always observed to be round. And generally, spheres always cast circular shadows, but if the Earth were a disk, if it were just a flat disk, we would expect that sometimes that disk, it seems likely, would be tilted a little bit with respect to the sun and would cast rather an elliptical shape shadow on the moon rather than a perfect circle. The fact that it was always observed to be a perfect circle during lunar eclipses suggests that it seems like it might be a sphere. Furthermore, a sphere in ancient Greek philosophy was considered one of the most perfect shapes, and so it made sense that something that was so central in the universe would be made of a perfect shape. So, the next kind of development in what the universe looked like and what Earth looked like was that the Earth is flat. The Earth is a sphere, and this is the model that Aristotle pushed forward and Ptolemy. And the other planets and the moon and stars they all circle the Earth in, pretty simple patterns. Of course, some of the planets actually seem pretty complicated if you watch them, but the stars have a rather simple motion. And so that's the model that Aristotle pushed forward, and we now accept that, except for a few flat Earth type people. Almost everyone accepts that the Earth is round now. One of the interesting developments or technologies associated with the Earth is, if the Earth is round, the natural question is, what's the size of the Earth? Or if you understand spheres, what's the radius of the Earth? And the first person to successfully measure the radius of the Earth in a very creative way was named Eratosthenes. And Eratosthenes had the following idea. It was known that there was this well in Syene, which was south of Alexandria on Earth, and at a certain time of year, when the sun was in the highest point in the sky, the sun shone down exactly into the well in Syene, this deep well. So you wouldn't, at most times of the day, you would see a shadow on one side of the well or on the other side of the well. But at this one time of day, at one point in the year, the sun shone exactly down and filled the bottom of the well, so there was no shadow on either side at the bottom of the well. So this was just sort of an interesting factoid that people knew about. And as people started talking about it, they realized, okay, up here at other locations, the same phenomenon on that same day of the year would not be true. For example, in Alexandria, there was an obelisk that was perfectly straight up and down from the surface of the Earth, and people, started looking on that same amazing day when the Syene well had this phenomenon where there was no shadow at the bottom, and the obelisk at Alexandria cast a shadow to one side, and that's sort of interesting. So now, looking at this side-on view of the Earth and imagining the rays coming from the sun, Eratosthenes realized that using a simple measurement, he could conclude what the radius of the Earth was, and that was the following thing. If he only measured the distance from Alexandria to Syene, and they actually had a huge expedition in which someone paced out the whole distance from Alexandria to Syene and reported it in units of stadia, which was one of the long distance units of the time. And one could measure this angle alpha right here, which is the same as the shadow is cast by the top of the obelisk with the direction the sun is coming. So this angle right here is alpha. That's this angle alpha because they're opposite angles. And that's the same as this angle alpha here, which is subtended from the center of the Earth to the 2 points on the surface. So, using a little elementary geometry and measuring this distance and measuring alpha, some of you have probably know the relationship arc length is equal to radius times this angle. S equals r theta is one of those relationships you see sometimes. And from that, you can figure out what theta is, or in this diagram, it's called alpha. I'm sorry, by measuring alpha, you can figure out what r is. And so in that case, you've measured the radius of the Earth, and Eratosthenes got a value that was very, very close to the modern value that we accept today. So it's just amazing to see how ancient peoples, knowing something realistic about the geometry of things, could figure out things. We'll talk about very shortly how you determine what the mass of the Earth is. Clearly, you can't weigh it on a scale. So that's another interesting question that's like that. Okay, so those are the Earth-centered models. The Aristotelian model was one in which everything rotated around the Earth. Earth was at the center of the universe still. The Sun-centered models, they're solving a problem of the motion of certain kinds of things. Not the stars, but the planets were rather complicated in the Earth-centered models. And so it seemed like, since circles were nice perfect shapes and the shapes of the trajectories of the planets were not necessarily simple trajectories in the Earth-centered models, it was realized that if you put the sun at the center of the universe rather than Earth, that the trajectories of all these planets would be rather simple with respect to the sun. So Copernicus had the most famous model suggested on this, where all the planets, including Earth right here, we've got Venus and Mercury there, and the other planets going outward, they're all supposed to go in perfect circles around the sun, and that simplified the description of their trajectories. Even though they appear complicated to us, that's only because we're looking from the point of view of a place that's not at the center of the universe. So that's a big deal to say the Earth was at the center of the universe and suddenly it's not. There were still some anomalies with the motion of the planets, and Kepler came up with an improvement to that, in which the statement is that these planets don't travel on perfect circles, but rather ellipses, which is giving up something, because circles are, in the minds of the Greeks, perfect shapes. Again, ellipses aren't quite so perfect. But Kepler had these 3 laws that described the motion of all the planets, apparently, perfectly. Oops. And here are the 3 laws, just in summary. We're not going to use them too much, but it's nice to know what they are. They're a direct consequence of Newton's laws of gravity, which we're going to get to very shortly in the next video. First law of Kepler's was that, okay, so here, let me just orient you to this. Here's the sun right here. Here's the motion of one planet shown in purple around the sun. So that's one trajectory of a planet. Here's a different planet going around the sun. So the first law is that the orbit of each planet around the sun is an ellipse, with the sun at one of the foci of the ellipse, at one focus of the ellipse. And what does the focus mean? If you're not familiar with analytic geometry, you may not remember what the focus of an ellipse is, but one way to intuitively see it is there's a way to draw an ellipse where you put 2 tacks on a piece of paper, into some solid thing underneath, and put a fixed length of string and keep that string taut with a pencil while you move the pencil around. Just keep the string taut so that one side is always going between the 2 pins, and so it forms a nice taut triangle like that, and you'll draw a perfect ellipse. The location of these pins are the foci of the ellipse. Foci is the plural of focus. So the claim is, if this is your ellipse, the sun has to be either here or here. That's what Kepler is telling us in the first law. Second law says that in a given time period on its orbit around, so if we wait a certain fraction of a year for Earth or something like that, a given planet sweeps out the same area for a certain time period, say a month, right? In a month, this area that's swept out by Earth here should be exactly the same as this area that's swept out in a month at this time of year. And the consequence of that is, well, since there's less distance here for the area to be the same, this distance has to be longer to kind of make up for it. And that means if these represent the same amount of time, this planet's going faster here, and it's going slower out here. So the planets go really fast when they're close to the sun, and then they slow down as they get farther away from the sun. So it's, the first law just tells the shape of the orbit. The second law tells something about the speed of the planet around the sun at different times of its year. The third law says something a little bit more mathematical, or it's a definite equation that it gives. If we call the planet's orbital period, and the orbital period means the amount of time it takes to make one complete circuit around the sun. If we call its orbital period capital T, and we call A its semi-major axis length. So what does the semi-major axis mean? Well, here's an ellipse in purple. The major axis is the one that goes through the longest direction across the ellipse, and the semi-major axis is just halfway from there. So it's from the center to one side. What is that distance? That's the semi-major axis length. If the ellipse were a circle, the semi-major axis length would just be the radius. So, we're going to spend a lot of time talking about circular orbits. So think of the semi-major axis as something that turns into the radius as this ellipse becomes a circle. Okay, so A is like the radius, T is like the period, and Kepler says that if you cube A and divide it by the square of T, you get something that is the same for every planet in the solar system. Okay, all the planets have different periods, and all the planets have different semi-major axis lengths. But if you cube A and divide by T squared, you get the same number for every planet in the solar system. And that number, by the way, was 3.36 times 10 to the 18th meters cubed per second squared for planets in the solar system. So those are Kepler's 3 laws of planetary motion, which was the state of the art at the time that Kepler was around. I gave the date, I can't remember what it was, but the date on one of the previous slides. Now that's still conceiving of the universe as a place where the sun is at the center of the universe. So the sun is a special place. It took over from the Earth being special not that long before. The last major development, and what's going to lead us into the modern or semi-modern description of gravity given by Newton, is this last section on, in Newton's conception and in Galileo's conception, there begins to be the sense that there is no center of the universe. There's no place that's right at the middle of the action. Okay. Galileo was a great scientist, but also a great inventor of instruments, and that he had, at his time that he was alive, there were other places that had telescopes, but he had the best telescopes in the world. So he could see things through his telescope that nobody else could see when he gazed up at the sky. And he, at one point, when he was really busy with astronomical observations, he published this book called The Sidereal Messenger, which relayed some of the things that he could see with his brand new telescope that was better than anything else that anybody could see. And it's kind of amusing, nobody publishes books like this anymore with these titles, but it's called, this of course is a translation, but the title page says, The Sidereal Messenger, unfolding great and marvelous sights, and proposing them to the attention of everyone, but especially philosophers and astronomers, being such as have been observed by Galileo Galilei, a gentleman of Florence, professor of mathematics in the University of Padua, with the aid of a telescope, lately invented by him, respecting the moon's surface, an innumerable number of fixed stars, the Milky Way and nebulous stars, but especially respecting 4 planets which revolve around the planet Jupiter at different distances, and in different periodic times with amazing velocity, and which, after remaining unknown to everyone up to this day, the author recently discovered and determined to name the Medicean stars. Quite a title page. All right, so here we are. Here he's talking about his observations of Jupiter. Let's just read a little bit above it and about this and see what he's thinking at the time. I was viewing the constellations of the heavens through a telescope. The planet Jupiter presented itself to my view, and as I had prepared for myself a very excellent instrument, I noticed a circumstance which I had never been able to notice before owing to want of power in my other telescope, namely, that 3 little stars, small but very bright, were near the planet, And although I believe them to belong to the number of the fixed stars, those, at least in the historic ancient view, those would be the stars that would be attached to the firmament and which just sort of rotated around. And even in Copernicus's model, around all of those planets, there still was thought to be a spherical shell of fixed stars that rotated around them. It really hadn't progressed a lot from the model of the firmament in the flat Earth models. Yet they made me somewhat wonder because they seemed to be arranged exactly in a straight line parallel to the ecliptic, and to be brighter than the rest of the stars, equal to them in magnitude. The position of them with reference to one another and to Jupiter was as follows, and he shows in his hand-drawn diagram, so this is from the actual document. He has hand-drawn diagrams in there where every night he's going up and looking at Jupiter, and he can actually see the finite size of Jupiter. It's not just a point of light in the sky like you see with your naked eye. He can see the size of Jupiter, and here he sees two of these fixed stars to the right as he views it through his telescope on a certain date. I can't read it here, but he's giving the date over here that he observed it. And then on the next day, 30th of something, I can't really read it, the next day he observes, here's Jupiter again. Now there's a third star that's appeared, and two of them to its left. And normally those fixed stars don't move relative to each other, so this is a very bizarre phenomenon. And here we go. This is the 30th of the month. Apparently the first was probably cloudy, and then on the second and the third and the fourth and the fifth, he's going on day by day and taking his data and showing relative to Jupiter, where are these stars? That's sort of curious. And Galileo starts to realize that, wait a minute, this would all make sense if the same way that the planets were orbiting around the sun in Copernicus's model or in Kepler's model, that Jupiter had its own little stars or moons that were orbiting around it, so Jupiter itself was a different center, and perhaps the Earth was a center with its own moon going around it, and so on. So that was a huge discovery at the time, and one that sort of, one of the many things that Galileo did that upset the church at the time, because there was an investment in the current cosmological picture of where we were in the universe, and this was upsetting information to that. But, Galileo's an enthused scientist, and he just goes ahead and says what he sees and what he thinks. Okay, so now onward to Newton's kind of idea of the universe. That was a huge break in that we could see that there's more than one center within the universe. 1584, Giordano Bruno proposed a cosmology without a firmament. In other words, forget about those fixed stars. I'm imagining an infinite universe in which each of those stars is just like our sun, and there are planets orbiting around them. Now, there wasn't a lot of direct evidence for this from astronomical observations, but it's an appealing idea in its own right? Well, we're not at the center of the universe, but wow, all these different stars we see are just like our star, the sun. The sun seems special, but maybe it's just like all these other points of light out there, and they all have their own planetary systems. Once Galileo's data was combined with that, it became harder and harder to argue that the sun at the center of the universe, there actually being a center of the universe, was an idea that made sense. And this is the beginning of the Newtonian kind of view of the universe, in which Newton sort of asserts that, like Bruno, space is an infinite container and it looks the same everywhere. So space here is just the same as space, many, many, many millions of miles away. There's no difference between it. There's no measurement we can do to tell the difference. It's just the matter that's flying through it that makes it appear different. And in addition to that, there's a gravitational force law among planets and among stars and planets that, in combination with his F net equals ma, second law of motion, determines how all those stars and planets move throughout space in time. And so that's kind of the beginning of the modern view of our universe. One of the benefits of having this view, and it was partially a mathematical view too, just like Kepler, Newton was writing down equations that allowed you to calculate exactly where things would be. He was able to unify things that before that time seemed very different, and that was, for example, the motion of the moon around Earth and the way things fall towards Earth. Normally, those were, previously those were thought to be two totally different phenomena, but now in Newton's model, he could show that, look, if you throw something off of a very tall mountain, of course fictionally tall, no mountain is this tall on Earth, but he's just imagining, throw it with a higher and higher tangential velocity component, at some point you might be able to throw it so it actually went into orbit around Earth. And so the motion of the heavenly bodies was connected with and unified with the way things fall toward Earth and go on parabolic arcs near the surface of Earth. Okay, so where we're on our way to now, that was a little historical side road there, but we're now going to learn more definite details about Newton's law of gravity and how it predicts all of these great things, and it's going to tell us exactly if I have two masses, mass m1 and m2, what's the force between them. Of course, they have to be equal and opposite forces according to Newton's third law, but what is that force? Well, it depends on how far apart they are, and it depends on the two individual masses. We'll come back with that.